Cookies sound good.
And so do I, but I have no cookies to give you.
Albertson's cookies.
Okay, so Nolan's bringing cookies on Monday, and we're recording this, so he just said it, and you're going to hear it on YouTube. You can hold him to it. Okay, ladies and gentlemen, when I left you on Tuesday, I asked you to find out how high or what the compression would be of the spring after it stopped moving. So we talked about spring compression. Let's just do a quick review. Hooke's law is F equals Kx, or F equals negative Kx, and it tells you the force you have to apply to compress a spring or the force the spring pushes back, either one. And then understanding that as you compress the spring with an F equals Kx, you multiply that compression by a distance, and the F equals Kx times the distance becomes work, because F is Kx, so work is Kxd. We just convert the d to an x, and we get 1/2 kx squared. The 1/2 has to be there because why? You're using the average force, okay? From not very much force to a whole bunch of force, as you increase the force, the 1/2 is there because the work is done by the average force, okay? If you don't want to use the 1/2, you're welcome to do calculus, but I don't want to do any calculus, so we're just going to make it 1/2 kx squared. If you're in calculus, you might recognize this as the differential of, or the integral of that. But anyway, area under the square, or under the triangle. Okay, so anyway, you're dropping your block from 1 meter high. The spring has a constant of 200 units of spring constants, and it's going to drop. The 2 kilogram mass is going to drop from 1 meter high, and it's going to cause the spring to go squish, and then the spring is going to push back, unsquish, because you know this, right? Just like in cartoons, or when you drop something on like your trampoline, it goes boing, 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 boing. Well, we want to know, what I want to know now is, what would the compressed spring height be when it stops moving? Okay? It's not going to return to its highest height. So let's just do the whole exercise over again so we can remind ourselves how this works. So, again, using the formula that potential energy is 1/2 kx squared, and k is 200, x is what we're solving for. What is the PE that we're solving for? So up here we have PE grav, and down here we have PE spring. And how do those relationships compare? They're the same, okay? So good. So we're going to set the PE grav equal to the PE spring, and then we're going to solve for x. So if you have it on your notes, good for you. If you don't have it on your notes, go ahead and do it, so we can basically catch ourselves up to where we were on Tuesday. Yeah?
Why is potential energy gravity?
Because when you drop the mass, it's going to go boo, and it's going to stop moving. It's going to basically, we're going to set the 0 point at where it stops moving. It's going to go boing, squish. So all the potential energy is going to be converted into potential energy in the spring.
You said the height was 1, right?
Apparently I did. Yeah, 1 meter. Yeah. You're asking me the answer to the lab question?
Yeah, no, it's like a question about it. It's not that. It's the resulting. I know it's like, it's the second one. It gives you all of them except for the resulting speed, and that's energy too. Mm-hmm. So potential energy 2 is just the resulting height?
Yes, from the resulting height, yeah. Okay. The potential energy 2 in that formula it comes from the resulting height of your
You
skater.
do all that, and then you get like K, then you get like 330 equals P2, and then you plug that 330 into the potential G gravity.
Or you're working backwards, yeah. So in the simulation, you're working backwards. So in that table, you have 4 of these 5 things. You just need to find the 5th.
Yeah, so I got P2, but it's 330 meters. Now it makes sense. So I plug it back into the P equals mg.
It's 330 joules, and you plug it in, yeah, and that'll give you the height.
Okay.
Yep. Okay, so anyway, spooling back 48 hours and 10 minutes, or 48 hours and 30 minutes. What was the height to which it got compressed, the maximum compression? Square? 0.45? Okay, so it gets squished 0.45 meters, and that is that squish right there. Okay, so the maximum squish is this X right here, and that is the 0.45 meters. Okay, so you drop the block, it goes boing, squish, and then it's going to start pushing back. Squish, 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 squish. And we want to know, when it comes to a rest, after it pushes back, what is going to be this X? How might I solve that?
That minus that.
This minus this?
No.
Okay.
I can figure it out. It's like math.
Use math? That's a great idea. Let's use math. What math? Physics math. Is it half of this? It's not half of this.
What's the formula? Confused on what exactly we're.
We want to find out what this, I wish I had the model. We want to find out what this squish is. So up here, it's uncompressed. We drop the block on it. The block is going to compress it, and then the spring is going to push back. And you know that the spring will push back, 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 and eventually it'll come to rest. So here it's come to rest. And it's come to rest to the point where this spring is compressed, but not as much as it was under maximum compression. I want to know how much spring it's going to, how much it's going to be compressed. Maybe if we draw a force diagram of everything that's going on here. How many? If I drew a force diagram of me.
I feel like you're gonna have to add the mass going in the right direction.
No. So if we were to draw a force diagram of me right now, how many vectors would be present? 2. Okay. So there's me. And we have a downward vector, and what is that downward vector? FG, good. And there's going to be, if that's the only one that exists, what would I have to be doing? Falling. But I'm not falling, so let's draw an upward vector, and what is that upward vector? F normal, good. Thank you to the floor for giving me F normal, and hopefully those things are equal, right? Yes. Okay, so back over here. Let's draw a force diagram. What 2 vectors should be represented? Force of gravity and force of normal. What is providing the force normal? The spring. So let's say force spring. Do I have a formula for force spring?
Yes. 1/2 kx.
No. Just kx. Good. So what we're basically doing is we're setting our Fg, and we're setting that equal to force of our spring. Fg is equal to what?
MGH.
Mg, just Mg. If it was MGH, it would be potential energy. And force spring is equal to?
Kx.
And can you now solve for K, or solve for X?
Yes.
Let's do it. Can we solve it?
Yes, we can.
Nice. Excellent reference. Sure. Why don't you think it's right? It has a maximum stretch of 0.4, so it's less than the maximum stretch, and it's more than 0. So Does this idea make sense? So, when you go bungee jumping, it's important that they understand this idea. That they don't measure out the bungee jump for your mass, they want to measure out the bungee jump for your potential energy. Because if they measure out the bungee jump for your mass, you're going to be like, hey, there's the water! And you're going to go splash, smack. Because if they measure out the 0.1 for just your weight versus the spring, then your kinetic energy will bypass that and you're going to keep going and going and going and splat. Does that make sense? So that's what's happening. So the 2 kilogram mass hits the spring, compresses it to maximum compression where the kinetic energy becomes the spring energy, and then the spring pushes back, and when it stops moving, the downward gravity is equal to the upward normal force provided by the spring. Why is this practical? Adam, you want to hear this? In a spring exercise, they will say things like dropped upon versus lowered down slowly. If something is lowered down slowly on a spring, the formula you're going to use is the Fg equal to the Kx. Does that idea make sense? Yep. If they say dropped upon the spring, then you're going to use the delta PE grav equals the delta PE spring. Okay, and there's a big difference whether the mass is lowered down on the spring until it stops or dropped on it. Okay. Similarly, if I had Torsten hold out his hand and I dropped the mass onto his hand, what's his arm going to do?
Nothing.
No. Okay, well, if it was Jimmy, Torsten would be like, boom. But if it was Jimmy, the mass would hit his arm, and what would his arm do? He'd go down and then he'd come back up. But if I just said, Jimmy, put out your hand, and I put this on here, he's just going to be like, boop, no big deal.
No,
okay?
I'm still going to go down.
No. Okay, well, Torsten wouldn't. Torsten would be like, no problem. Okay, question. Yes. So if the question in the AP says a mass is dropped upon a spring, then you're going to do the potential energy of the spring equal to the potential energy of the grav. If it is lowered down on the spring, then you're just going to set the mg down equal to the kx up. Does that make sense? Yeah. Then let's finish our lecture. Any questions? All right. So the last thing we have to talk about is power, but it's really, really simple. We'll talk about collisions next time. I briefly mentioned what a collision is. There are 2 types of collisions. The first type of collision is called an elastic collision, where objects don't deform. And the second type is an inelastic collision, where they do deform. And we're going to talk about collisions next time. So power is the rate at which work is done. Power is the rate at which work is done. And it's really, really simple. It just has the formula, work over time. I got a little optimistic and I scheduled a fun lab for today, but we're going to do the fun lab on Monday.
Dang it.
Yeah, power pulleys. So wear your workout gear. You might sweat. Yes. You're going to lift masses as fast as you can. You're going to like, how much power can I produce? You're going to lift masses as fast as you can.
I'm good at those.
Yeah. Math classes usually do it on stairs. They run up and down stairs as fast as they can. But I don't want the bloody noses, so we're going to use masses instead.
I want juice. So you do too.
You want juice to do it?
That juice on my
Okay, so the unit of power is the watt, and the watt is defined as a joule per second. So I'm kind of jealous of European motor companies or motor videos like on YouTube, because they give the power outputs of engines in kilowatts, which is totally cool. We still use the stupid horsepower. There's 700 horsepower per watt or 700 watts per horsepower. It's one of those two. Yeah, I love how they give us engines in kilowatts. So the kilowatt is usually what we normally use when we talk about normal things in real life. The watt is a very small unit. It's a joule per second. To give you an idea how small a watt is, yeah, so this 2 kilogram mass has a weight of 20 newtons. If I lift my 20 newtons 1 meter in 1 second, that's 20 watts. It's like, 20 watts. And you're like, that wasn't hard at all. So the watt is very, very small. Okay, so this is kind of cool. Actually, I'm just going to make this go away. But I'll bring it back up in a second so you're paying attention to me. This weekend, have your parents show you their power bill. It's kind of neat because you're going to have to eventually pay for power when you move out of the dorms. So just get ready for that. Understand that power is not free. So, yeah, it's not free. So when you go to the dorms, you can use as much power as you want because it's all paid for by the school. But eventually when you move out to your apartment or your small house, your first apartment, you will eventually have to pay for power in addition to...
My Wi-Fi? Right?
No. Yeah, in addition to water, cable, internet, and toilet paper, power costs money. When you all find this when you move out to your first apartment. But it is fun. But anyway, when you look at your power bill, you'll notice power is sold to you in kilowatt hours, which is actually kind of cool. It'll say kW hour. Power is sold to you in kilowatt hours, which is 1,000 watts multiplied by 3,600 seconds. So you don't actually buy power from a power company. In fact, about 15 years ago, Nevada Power changed their name to Nevada Energy. Just because they were like, we got to make the physicists happy. Because you don't actually buy power from a power company, you actually buy energy. Because a watt is a joule per second. And a joule per second times a second is a what? A joule, right. So when you buy a kilowatt hour from your power company, you're actually buying 3.6 million joules. It's not a bad deal. 3.6 million joules for about 11 cents.
Wow.
Yeah.
Especially in Boulder
What
City.
a deal.
I guess Boulder City got more expensive recently, but
Recently, it's
yeah.
less expensive than everywhere else.
Fair enough. I have a solar array, so I only pay for what I make in my solar array. Yeah, it's awesome. But anyway, so yeah, 1 kilowatt hour is 3.6 million joules. Now, why is that useful? And this is why this is useful. Are you ready? When your parents complain about all the power you and your Xbox are using, you can do the math. So let's do the math.
Oh, yes. Here we go.
Here's something practical that you can use this weekend when your parents complain about all the power you're using.
It's not power, it's energy, Mom.
Oh, you're going to love this, though. Okay? So, okay, your Xbox. I found out that the Xbox One X uses about 150 watts, and the PS4 Pro is about the same. So let's just go ahead and say 150 watts for your Xbox or your PS4. Yeah.
Would older systems use more or less?
They are. Yeah, older systems are actually less efficient. The original PS3 used almost 200 watts.
What?
Because
PS2.
that might actually use, it's hard to say. So you realize the chips are constantly getting smaller, and as they get smaller, they have to use less power to do a command.
Is that the Xbox?
Xbox One is about 150 also. Yeah, so the Xbox One X is more powerful, but it uses about the same amount of energy or less. Okay, guys, here we go. So your television, I only own plasmas, and plasmas are massively inefficient because they're really, really bright and they look great. But you probably have an LCD TV. A general LCD TV uses about, for like a 55 or a 60 inch, they use about 250 watts. About twice that. Yeah. Yeah, plasmas are massively inefficient. OLEDs are the best. But anyway, moving on. So if you're going to have your TV on, oh, and your router uses about 10 watts, so we'll just ignore it. Okay, your wireless router, we can just ignore it. So your game system and your television use about 400 watts. You ready? If you use it for 1 hour, you are using that for 60 minutes multiplied by 60 seconds. So far, so good?
Yeah.
Okay. So to use your system for an hour, you're going to burn 400 watts, 60 minutes by 60 seconds. How many joules are you using in 1 hour? This is where you bang on your calculator. I can do it in my head, but I want you to do it too.
6 equals 1 million. 24 times 6.
14 times.
You're getting there.
1,140,000.
So about 1.4 million joules, or about 1.4 times 10 to the 6 joules. Not even close. So a kilowatt hour is 3.6 million joules, and it costs you about a dime. So next time your parents are complaining about how much power you're using by using your TV and your Xbox, just flip them a quarter and say, I'm good for the next 5 or 6 hours.
When you buy it, it might get better.
Yeah.
Yeah.
A 60 watt incandescent light bulb uses 60 watts. No, this is a really good point. So the old style light bulbs with a little filament, a 60 watt light bulb uses about 60 watts. A CCFL that is 60 watt equivalent uses about a third of that. And then a LED that's 60 watt equivalent uses about a fifth of that. So a 60 watt equivalent bulb in an LED uses about 10 watts.
So like they always told us in biology to like unplug our stuff. Does that take energy when we don't unplug it?
If it's unplugged, it's not doing anything. If it's not drawing anything out of the wall.
Well,
But
like if it's not like our chargers,
right,
it's using stuff.
almost nothing. Yeah, and this is another thing. I read in the same article about the Xbox One X. Its standby mode, so it can download games, is 10 watts. Your TV's standby mode, so it can turn on with your remote control, is about 2 watts. And your phone charger, 2 watts.
I still feel like I should unplug it.
Okay, Noah's got a legit question.
Alright, if you take a power strip, put a cord in it, and plug the cord into itself, is it using energy?
It is actually. It depends on how smart the thing is. Most likely, the cord is smart enough to not put any power into that outlet because there's nowhere for it to go. But if it's a bad cord and it has enough resistance, it will actually heat up. So I strongly recommend you don't do it. Okay. If it's a smart enough power cord or smart enough power adapter, it'll be like, the electron has nowhere to go. But if it's not, that cord will become like a toaster element and it'll just heat up. So don't do that. Yeah.
So you said you had solar. So do you know how much that helps?
It's really kind of complicated. Basically, I have a deal where I pay for the solar I make up until a point, and then I don't pay for it after that. Everything else is free, basically free power. But I have an old system that has an old program or an old plan. Newer plans, they basically give you 95% of your whatever power you make when you give it to your neighbor. Yeah, so I don't get money back. I get energy credits, which then I can use in like August and July to buy power back at a 1-to-1 ratio. So for me, I basically pay 11 cents a kilowatt hour for a minimum amount to produce, and everything else I produce above that is free. It's pretty cool. So sunny days are awesome for me because eventually I'm like, hey, I hit my maximum and I don't have to pay anymore.
Every day is awesome for you.
It's nice, yeah, when it's nice and sunny, because again, I pay for a certain number of kilowatt hours, and that's what I always get. I get a minimum amount. Anything I make above that, free to me.
The sun's still out, but so it's better in the summer. It doesn't matter because the sun's still out in the winter.
Yeah, I can't. The way Nevada Energy works, I can't make enough on my roof to pay for what I'd be using in August and September and July, but I build up energy credits in the wintertime. Like right now, my air conditioner's not on, and I'm basically building up energy credits, like 100 energy credits every week, which then I can use later on. It's pretty great, but again, financially, I'd have to know what Boulder City is to actually know if it makes sense in Boulder City. But if your parents want to go solar, have them give me a call. We'll chat. I'll walk them through it and have them get a good deal. So anyway, yeah, there we go. So you guys know how to do power, but this is just a fun exercise. A winch and a poi lifts a So you can quickly determine which of these is most powerful. So just bang on these calculators and find out which of these 3 devices is more powerful. A soccer player's foot, a winch, or a basketball player's arm.
It's the last one. The last one's 8.